Hello everyone. This is a training about response spectrum, one of the Midas training series. I hope all of you will enjoy the training. The ground motion due to earthquake is measured in the form of acceleration. 3 accelerograms are recorded simultaneously along 3 mutually perpendicular directions to capture the complete oscillation of the ground at a location. The ground acceleration shown here is obtained from El Centro site in 1940. In the eigenvalue training, we learned that if the frequency of loading comes close to the frequency of fundamental natural mode of structure, the response of structure will be much higher than the static response because of resonance phenomena. So, you may want to know the frequency of this ground acceleration. Can you see the frequency of this loading? It is difficult from this graph. We can find it using Fourier Transform, which is available in Midas. In order to apply Fourier Transform in Midas, we apply the ground acceleration to the structure and generate acceleration graph for the fixed support. From the acceleration graph, we convert this form time domain to frequency domain. In this graph, the horizontal axis is the frequency, and the vertical axis is the amplitude of waves. Now, we can see from this frequency spectrum that the ground motion is made up of many frequencies, rather than a single frequency. Among them, the frequencies in the range between 1 Hz and 5 Hz have larger amplitudes. This means that the structures whose fundamental frequencies are 0.2 seconds to 1 second will be most damaged due to this earthquake. Approximately, these fundamental periods correspond to 2 to 10-story buildings. That is why the damage of the structures is usually severe in the low-story buildings and minor in the tall buildings. You may have seen this frequently. This is another type of representation of this seismic action called response spectrum. This defines the relationship between peak acceleration and period of SDOF system. Usually, 5% damping ratio is assumed. For the design of the new buildings, this is more frequently used than acceleration graph of ground motion. Generally, this may be either given in the design codes or obtained from a particular ground motion. Do you remember the equation of dynamic equilibrium for earthquake loads? We learned that total acceleration is the sum of ground acceleration and relative acceleration, and the total acceleration generates inertia force. The acceleration given in the response spectrum corresponds to the total acceleration, not relative acceleration. For the design of structures, generally we use response spectrum given from the design code. But we will see how the response spectrum can be obtained from this ground motion in order to understand how response spectrum is determined. This is the same ground motion used in the previous slide, 1940 El Centro site. These are SDOF systems with various periods of vibration. The damping ratio is assumed to be 5%. We apply the ground motion, which was shown in the previous slide, and find the total acceleration at the location of mass. The peak total acceleration for the SDOF system with the natural period of 0.55 seconds is 0.93 g, and it occurs at 2.2 seconds. For the system with a natural period of 1 second, the peak acceleration is 0.52 g. At the same time, at the time of 4.4 seconds. We can draw the graph using the peak accelerations and natural periods of all SDOF systems. This is how we can generate response spectrum. Or we can obtain the response spectrum simply from the ground motion using the seismic data generator in Midas. This is called Pseudo acceleration response spectrum. The response spectrum obtained from time history analysis in the previous slide is called true acceleration response spectrum. The pseudo acceleration response spectrum is almost same as true acceleration response spectrum. Once this response spectrum is available, we can find the base share of any SDOF system without performing time history analysis. For example, the mass is 100 and the natural period is 1.0. The acceleration read from the response spectrum is 0.52 g. So the base share will be 100 times 0.52 g or 52 g. All other response displacement, forces, reactions can be obtained by applying the base shear force 52 g to the level of mass. Design response spectrum is derived from the response spectrum of many individual ground motions. The design response spectrum is the smoothened envelope of all response spectra of the ground motions for which the building is expected to be designed. We have seen that for the SDOF system, the peak response can be determined directly from the response spectrum for the ground motion without carrying out a time history analysis. Now, let's see how the peak response of MDOF system can be calculated from the response spectrum using this example. As we learned in the eigenvalue training, the response of MDOF system is the combination of the responses of each natural modes of the MDOF system to the dynamic load. So, as the first step, we need to determine the natural periods and natural modes of vibration. As the second step, we read the acceleration from the response spectrum corresponding to natural periods and damping ratio. Do you remember modal participation factor? When we decompose the equation of MDOF system into SDOF systems, the ground acceleration is scaled by this factor in the SDOF systems. If the ground acceleration is scaled, the relative acceleration also becomes scaled by the same factor. So, the acceleration from response spectrum should be scaled by modal participation factors. Then, the scaled acceleration for mode 1 and mode 2 are determined like this. As the third step, we need to compute the equivalent static lateral forces. The static lateral force for each floor will be determined by floor mass times scaled acceleration times floor mode shape. For each floor, mass times mode shape times modal participation factor gives effective modal mass. So, you can also calculate equivalent static lateral forces by effective modal mass times acceleration, directly read from response spectrum. Midas provides this effective modal mass. As the fourth step, compute the floor displacements, story drifts, story forces, and element forces by static analysis of structures subjected to the equivalent static ladder forces for each modes. As the final step, determine an estimate for the peak value of any response by combining the peak modal values according to the SRSS rule or CQC rule, because unlike mode superposition method with time history analysis, the peak modal values in response spectrum analysis are not concurrent results. The CQC rule should be used if the natural frequencies are closely spaced. This is the modal combination for the floor displacements according to the SRSS rule. This is for the element forces. As you see in the diagram for modal combination, the moments are always positive because of SRSS rule. There are some mistakes frequently made by the user about the response spectrum analysis. First, it is about the reactions. They might think the summation of reactions of all individual supports should match the total reaction, just like static analysis results. This is not true. In response spectrum analysis, any response is calculated from the modal responses by modal combination rule. Nodal reaction is calculated from the nodal reactions of each modes by modal combination, and total reaction is also calculated from the total reactions of each modes by modal combination rule. So, the summation of reactions of all individual supports does not match the total reaction or base share of the structure. For the same reason, story drift should not be calculated from the floor displacements obtained from modal combination. Instead, story drifts for each mode should be first calculated from the modal floor displacements, and then the modal story drifts should be combined by modal combination rule. The capacity of structural system to resist seismic actions in the nonlinear range generally permits their design for resistance to seismic forces smaller than those corresponding to a linear elastic response. To avoid complex inelastic structural analysis in design, the capacity of structure to dissipate energy through mainly ductile behavior of its elements is taken into account by performing an elastic analysis based on a response spectrum reduced with respect to the elastic one. This is called design spectrum. The reduction is accomplished by introducing the behavior factor in Eurocode or response modification factor in ASCE code. In this figure, the actual seismic force is reduced by behavior factor and we perform elastic analysis. So, the base shear can be reduced to the magnitude of actual nonlinear behavior without performing nonlinear analysis. The displacement is also reduced by the same factor. But this is not the actual nonlinear behavior. So, we should multiply the displacement obtained from elastic analysis by behavior factor in order to get the actual displacements. The damping ratios are typically assumed to be 3% for steel structures and 5% for concrete structures. In response spectrum analysis, we can simply define the same damping ratio for all the modes using the Modal method. Mass and stiffness proportional method, or Rayleigh method, is rarely used for response spectrum analysis. Rather, it is usually used in the time history analysis. We will learn about this in detail in the time history training. If you select strain energy proportional method, the damping ratios for each modes are determined by the program based on the strain energy of each modes. This is useful in case when two or more different materials are used together in a structure. For example, the damping ratio for some part of structure is 0.03 and the other part is 0.08. Then, we define different damping ratios for different parts using the group damping function and select strain energy proportional method. After performing analysis, we can check the calculated damping ratios for each modes like this. The peak acceleration of SDOF system will be decreased as the modal damping ratio is increased. In order to consider this change of acceleration depending on different modal damping ratios, we need to define elastic response spectrum with different damping ratios. For example, we define three elastic response spectrums with 2%, 5%, and 10%. From the response spectrum load case, we select all three functions and select interpolation method of spectral acceleration data. Then, the spectral acceleration will be determined depending on the modal damping ratios calculated by the program. As for the correction by damping ratio option, the program will calculate spectral acceleration for various damping ratios, even when only one response spectrum function is defined. When we use design response spectrum for the design of new buildings, damping ratio is not required. Do you know why? As I mentioned in the previous slide, we use the behavior factor in Eurocode and response modification factor in ASCE code to reduce seismic force in the response spectrum analysis in order to consider actual nonlinear behavior of force-related results. These factors also account for the influence of damping ratios for various materials and structural systems. So, damping ratio is not included in the design response spectrum functions. This is all for the response spectrum training. Thank you for listening.